Good morning, everyone. Today, I'm excited to share with you our research, LAGON, efficient equalization for mixed-size circuits with linearized augmented Lagrangian method. On behalf of my collaborator, 春元照、作栋章、智雄底、易波林、润生王, and Ru Huang from Peking University and Southeast Jiaotong University. Let's dive into the detail. Here is the outline of our presentation. In modern AC design, mixed-size circuits are becoming increasingly popular. By combining higher and smaller cells, we can optimize power, performance, and area. Higher cells enhance the performance and routability of critical paths, while smaller cells improve area efficiency and reduce power consumption in non-critical logic. However, this desired approach also brings new challenges. Legalization is a crucial step in the design flow, as it eliminates violation after global placement, and it can impact downstream routing and overall performance. In mixed-size circuits, we face several challenges. This includes site alignment, ensuring cells are overlap-free, drawing the crossroad shapes, power and ground alignment, fence regions, as spacing, and pin access. Solving this challenge efficiently is the key motivation behind our research. Previous work on mixed-size circuits can be categorized into intra-rows and inter-row methods. Intra-row methods such as integer linear programming and linear complementary problem consist of row assignment and then intra-row optimization. However, they have limited vertical movement space during optimization. Inter-row methods, like those based on never flows or integer linear programming, offer higher flexibility but are more computationally expensive. Existing methods struggle with complex constraints and scalability, creating a gap that our algorithm aims to fill. So in this work, we propose LAGON, an efficient equalization method for mixed-size circuits. We use a linearized augmented Lagrangian methods, which enable efficient vertical and horizontal movements. We also introduced the block gradient design methods for parallel cell updates and a triple-fold partitioning technique for GPU efficiency. Experimental results show that our algorithm achieved 6 to 36 quality improvement and up to 94 times speedup with less than 0.5% quality degradation. So let's dive into the detail. The LAGON algorithm follows a three-stage workflow. In the first stage, initial equalization, we move cells with minimal displacement, ignoring overlaps. This quickly gets the cell into a rough position. In the second stage, we optimize the displacement and eliminate overlaps using the augmented Lagrangian method. Finally, in the refinement stage, we perform a strict no-overlap optimization to further improve the placement quality. The key components of the algorithm include the linearized augmented Lagrangian methods formulation, block gradient design for parallel updates, and GPU-friendly partitioning. The objectives of our augmented Lagrangian formulation is to minimize cell displacement while satisfying various constraints. We define the displacement cost function and introduce binary variables to represent the placement of a subcell at different sites. By introducing select variables and Lagrangian multiplier, we realize the long overlap constraints through iterative solving and the multiplier updating. Based on the KKT conditions, we gradually approach the optimal solution. This formulation can balance displacement and constraint satisfaction. To solve the optimization problem in the augmented Lagrangian iteration, we use the linearized proximal gradient method. We first define the proximal mapping operators and simplified it to a linear operators to find new cell positions. By incorporating the gradient of the cost functions and considering routability constraint as a penalty term, we calculate the final cost function for each candidate position. For each cell, we enumerate the candidate positions nearby through the diamond search method, compute the cost for displacement, overflow, and technology issues, and select the position with the minimal cost. These methods enable us to efficiently search for the optimal cell placement while taking into account for both the displacement and the constraint. The block gradient design methods aim at parallelized cell updates without sacrificing conversion speed. We use triple fold partitioning to divide the layout into non-overlapping subregions. Each subregion has a corresponding cell subset, and we update cells within each subset in parallel. By rotating the parallel scheme, we ensure that all cells have the opportunity to be updated. This approach, combined with GPU acceleration, significantly speeds up the legalization process. For GPU acceleration, we design kernels with one grid per subregion and multiple threads for candidate selection. Each thread calculates the cores at a different candidate position, and the results are stored in shared memory for fast communication. We use parallel reduction to find the minimal cost position. This two-tiered parallelization strategy at block and thread level fully explores the GPU parallel computing power, making our algorithm highly efficient for large-scale designs. So we will show the experimental results. In our experiments, we use two sets of benchmarks, ICCAT 2017 benchmarks with runnability and fence region constraints, and the modified ISPT 2015 benchmarks with Munian cell designs. We evaluate our methods using metrics such as the quality score, which combine HPWR variation, weighted average displacement, maximal displacement, and the number of design rule violations. We also compare the runtime and the speedup. Our experiments was conducted on a platform with one NVIDIA GPU and two CPU. Compared with the state-of-the-art methods on ICCAT 2017 benchmarks, our algorithm showed outstanding performance. We achieved about 6 to 36 improvement in the overall quality score, along with up to 3 times speedup. Looking at the breakdown, we have about 13 to 34% improvement in HPWR variation, about 4 to 33% improvement in weighted average displacement, and about 10% improvement in maximal displacement. This demonstrates the effectiveness of our methods in optimizing placement quality. When tested on large-scale designs for the modified ISPT 2015 benchmarks, our algorithm also performed excellently. It is about 2 to 5 times faster than the state-of-the-art methods and has about 1 to 28% better displacement. In 3 out of the 5 cases, we can complete legalization in less than 10 seconds. The combination of GPU parallelism and efficient partitioning enable this excellent scalability for large-scale designs. In the ablation study of the triple flow partitioning, we found that our algorithm with triple flow partitioning achieved about 19.4 times speedup compared to the no partitioning, with less than 0.5% quality loss. Regarding the runtime breakdown, the augmented Lagrangian method-based legalization stage took about 39% of the total runtime. The initial legalization took about 3%, and the legalization refinement stage took about 5%. Understanding this breakdown helps us to further optimize the algorithm. So in conclusion, in this work, we proposed Lagum, an efficient legalization for mixed cell height circuits. Our linearized augmented Lagrangian formulation, block gradient descent, and triple fold partitioning technology contributed to its high performance. For future work, we plan to explore for advanced parallelization strategy to further improve the efficiency of our algorithm. Thanks for your attention. If you have any question, please feel free to ask. You can also contact us at the provided email address for more information.